In this video, we're going to learn how to approximate the area under a curve using rectangles and then see how taking a limit gives the exact area. We'll go through an example using right-hand endpoints, left-hand endpoints, and midpoints, and then find a general formula for the area under a curve. We'll also look at two examples, one where we write an area as a limit, and another where we're given a limit and find the region it represents. Be sure to download the free guided notes to follow along, highlight the formulas, and work through the examples with me. Let's start by learning how to find the approximate and exact area under a curve using rectangles. The area problem consists of finding the area under the curve y is equal to f of x, shown down here in our graph, from x is equal to a, where this is a, to x is equal to b. We can find an approximate area by dividing our region into small rectangles and then finding the sum of all the areas of the rectangles. We can find the exact area by dividing the region into an infinite number of small rectangles and then using a limit to find the sum of all the areas of the rectangles. When we approximate the area under a curve, the width of each rectangle is usually the same, and the height depends on the function y is equal to f of x, shown down here in our graphs. There are three common ways to approximate the height of each rectangle. The first is by using right-hand endpoints. The second is when we use left-hand endpoints. And then the third, which is the most accurate, is when we use midpoints. We're going to walk through an example where we're going to estimate the area under the graph of a function. In our example, we're going to estimate the area under the graph of y is equal to 16 minus x squared. That's just a parabola that's curving downward from x is equal to 0 to x is equal to 4. And we're going to use four rectangles, and we'll use right-hand endpoints in part A, and then in part B, we're going to use left-hand endpoints, and in part C, we're going to use midpoints. I went ahead and graphed our curve, and let's go ahead and let's do part A. For part A, we are using right-hand endpoints. These are these points right here to approximate the height of each rectangle. And notice that there are four rectangles. Let's start by making a note that the area of each rectangle can be approximated by the height times the width. Notice that since we have four rectangles and our region is from 0 to 4, the width of each rectangle is going to equal 1. Our height is going to be approximated by our function y is equal to 16 minus x squared, and we're going to let that equal f of x. That will just help when we put it into our formula. Our area is approximately the area of our first rectangle, and this point is f of 1. So we have our height, f of 1, times our width, which is 1. And then our second rectangle has a height of f at 2. So we add on f of 2 times 1. And then our third rectangle has a height of f of 3. So we have f of 3 times 1. And then our last rectangle has a height of f of 4. We'll go ahead and put it down even though f of 4 is equal to 0. So we have f of 4 times 1. Now let's plug in what our function is. Our function is 16 minus x squared, so f of 1 is just 16 minus 1 times 1, which we won't write down. And then our f of 2 is 16 minus 2 squared. And then f of 3 is 16 minus 3 squared. And then we'll go ahead and put down that our f of 4 is 16 minus 4 squared, even though that's 0. Now let's see what this gives us. This is 15 plus 16 minus 4, which is 12. And then we have a 16 minus 9, which is 7. And then we have our 0. So we can say that our area is approximately, let's see, we had 27 plus 7, so that is 34. We can say then that when we use right-hand endpoints and we have 4 rectangles, our area is approximately 34. Now we're going to do the same thing, except in part B, instead of using right-hand endpoints, we're going to use left-hand endpoints. Let me go ahead and highlight those. There's our first one, second one, third one, and fourth one. Just so that we have it, I'm again going to write down that y is equal to 16 minus x squared, and that is our f of x. Now let's write down our formula for our area. It is approximately the height at our first endpoint. So this is going to be f at 0. So we have f at 0 times 1. And then our next one is f of 1. That gives us f of 1 times 1. Hopefully you're getting the hang of this. This one is f of 2. So we have f of 2 times 1. And then our last one, we have f at 3 times 1. Now let's go ahead and put this into our function 16 minus x squared. Our first one gives us 16 minus 0 squared. We're going to ignore the ones for the width. And then our next one is 16 minus 1 squared. And then we have 16 minus 2 squared. And then our last one is 16 minus 3 squared. Our area is then approximately 16 plus 16 minus 1 is 15. And then we have 16 minus 2 squared. So we'll write that down as 16 minus 4. And then our last one, we have 16 minus 9. This is approximately 16 plus 15, that's 31. And then we have 16 minus 4 is 12. And then 16 minus 9 is 7. So our area is approximately 31 plus 12 plus 7, that is 19. Our area then is approximately equal to 50. Let's now look at part C. For this part, we are going to approximate the height using midpoints. This is harder than left-hand endpoints and right-hand endpoints because we usually have fractions. Let's go ahead and let's put down what the x value is for each of our midpoints. Our first one is going to be 1/2. Our second one is going to be 3/2. Our third one is going to be, 2 plus 1/2, so that's 5/2. And then 3 plus 1/2 gives us 7/2. Now we'll write down that y is again equal to 16 minus x squared, and that is f of x. Now we can go ahead and write down the formula for our approximate area. It is going to be f at our first midpoint, which is 1/2, times our width, which is 1, plus f times our second midpoint, that is at 3/2, times 1, plus f at our third midpoint, which is 5/2, times 1, and then our last one is f at 7/2, times 1. Let's now use our formula that f is 16 minus x squared. Our first one gives us 16 minus 1/2 squared, so that's 16 minus 1/4. And then we have 16 minus 3 halves squared, so that's minus 9 over 4. And then our next one is 16 minus 25 over 4. And our last one is 16 minus 49 over 4. So you can see it gets a little bit complicated because we end up having to add fractions. One thing that is going to make our calculation a lot easier is if we go ahead and we add all 4 of our 16s together. So this is going to be 16 times 4. And then we're going to subtract 1/4, 9 over 4, minus 25 over 4, and minus 49 over 4. Let's see what this gives us. 16 times 4 is 64. And let's do this in pieces. Let's look at these pieces first. We have minus 1, minus 9. That gives us minus 10. And then minus 25. So that is minus 35 over 4. And then our last one is minus 49 over 4. And this is 64 minus 84 over 4. That's really nice because 84 over 4 is 21. So our area is approximately 64 minus 21. And that gives us an approximate area of 43. Now that we're done with these calculations, I want to do a little comparison. I actually went ahead and calculated the exact area. That can be done using integration, and we're going to get to that in some upcoming lessons. Let me just write down that our exact area, I'm just looking for an open space here, is equal to 128 divided by 3, and that is approximately 42.67. So let's go ahead and let's compare our approximations to this exact area. Let's go back up here to part A. We got that our area was approximately 34. That is less than our exact area, and we expect that because if you look here at our graph, you can see that our rectangles are smaller than the area under our blue curve. Let's now go to part B. I'm looking right here. Our approximate area was 50. That is bigger than the exact area. And that also makes sense because if you look at our graph, the area under our rectangles is bigger than the area under our curve. And then for our last one, down here at the bottom, our area is really close to our exact area, which is pretty amazing considering we only used 4 approximating rectangles. Let's learn about the general formula that we can use to find an approximate and exact area under a curve. We are going to find the area under the curve y is equal to f of x. That curve is shown down here in our graph. And we're going to find the area from x is equal to a. That's down here on our left. And then we're going to go to x is equal to b, which is down here on the right. It is very standard to let n be the number of rectangles, and that's why we notate our right-hand endpoint as x sub n, and then delta x, shown up here on our graph, is just the width of each rectangle. Now we need to find a formula for the width, delta x, of each rectangle. It is equal to the width of the region under the curve, that's b minus a, all divided by the number of rectangles. Now we need to find a formula for each point between a and b. We'll start with our first point, and we're going to label it x sub 0, and it's equal to a. A is the left-hand endpoint. And then our next point, x1, is just going to be a plus delta x. And then x2 is going to be a plus 2 delta x. And then there may be a lot more rectangles, but then we're going to get to a general point, and we're going to call that point x sub I, and it is equal to a plus I delta x. The approximate area under the curve y is equal to f of x is equal to a, and it is the sum of all the rectangles. We're now going to write down a formula for the sum of all these rectangles. Our area is approximately r sub n. We call it r sub n because for this formula, the height of each rectangle is going to be approximated using a right-hand endpoint. Our formula then is f of x1 times delta x. Let's go back up here. That's just this height right here. That's f of x sub 1, and then our width is delta x. And then we have the same thing, f of x2 times delta x, all the way up through f of x sub n times delta x. Notice that all of these terms have a delta x in it, so we can combine them and we can pull out our delta x. This formula is really long, so what's done in practice is that this formula is written using what's called summation notation. I have a video on that if you need to review that. It's just a compact way of writing the sum of a bunch of terms. We can then say that the approximate area under our curve, A, is approximately r sub n, and it's the sum from I goes from 1 to n of f of x sub I times delta x. So it's just f of x1 plus f of x2 all the way up through f of xn, and all of those get multiplied by delta x. We can then find the exact area because we know all about limits, and we can say that our area is equal to the limit as n goes to infinity and I goes from 1 to n of f of x sub I times delta x. So basically, we are doing the same thing as in the approximate area, but now we have an infinite number of rectangles, and we're finding an exact answer when we let n go to infinity. We're going to walk through an example where we are given a function and we want to find an expression for the area under the graph of our function as a limit. I'm going to show you exactly how to do this problem. When I have taught this problem in class before, students really struggled with it because it's a multi-step problem and it involves some formulas that are a little complicated. The function that we're given is f of x is equal to 5x all divided by x squared minus 1, and we're told that x is greater than or equal to 1 and less than or equal to 3. The way to solve this problem is to start by writing down the formula for the area under the graph of a function using limits. That formula looks like this. It's a is equal to the limit as n goes to infinity, the sum from I goes from 1 to n of f of x sub I times delta x. What we need to do now is we need to find two things. We first need to find delta x, and then we need to find x sub I. You always want to find delta x first. Let's write down our formula for delta x. Delta x is equal to b minus a all divided by n. B is our right-hand endpoint, and in our case, that's 3. And then a is our left-hand endpoint, and that's 1. And n is our number of rectangles, and that just remains as n. So we have delta x is equal to 2 all divided by n. Now let's find x sub I. The formula for x sub I is that x sub I is a plus I delta x. We can substitute in what a and delta x are, and we get x sub I is equal to a, which is 1, that's our left-hand endpoint, plus I, and we just found that delta x was 2 over n. I am going to highlight both of these formulas because we are going to need these. There's delta x, and there's x sub I. Now what we're going to do is we're going to substitute all of this back in to our formula for a right there. A then is equal to the limit as n goes to infinity, the sum I goes from 1 to n, f of x sub I. So that now is f, and we're going to plug in that x sub I is 1 plus 2i over n. Notice I changed the order there. Typically, the constant comes before the I. And then we're going to multiply this by delta x, which is 2 over n. Now what we're going to do is we're going to substitute in that f of x is 5x all divided by x squared minus 1. This gives us a is the limit as n goes to infinity, the sum I goes from 1 to n, and now we're going to substitute in 1 plus 2i over n for each value of x. I'm actually going to make a bigger parenthesis here. I'm going to need that. So we have 5 times 1 plus 2i over n in our numerator, and then in our denominator, we have x squared. So this is 1 plus 2i over n squared minus 1. And that gets multiplied by 2 over n. And that's all we need to do. And this is our final answer. We are going to now walk through an example where we are going to determine a region whose area is equal to a limit that we're given. The limit that we're given is right here. It is the limit as n goes to infinity of the sum from I goes from 1 to n of 4 divided by n times the quantity 5 plus 4i divided by n raised to the 10th power. This is a challenging problem, so we're going to work through it step by step so you'll know exactly what to do. You want to start by writing down the formula for the area under a curve y is equal to f of x from x is equal to a to x is equal to b. That area is given by the limit as n goes to infinity, the sum from I goes from 1 to n of f of x sub I times delta x. You also need to write down the formula for x sub I and delta x. X sub I is equal to a plus I delta x, and then delta x is equal to b minus a over n. Our region is the area under the curve y is equal to f of x from x is equal to a to x is equal to b. That means that we need to find f of x, a, and b. To find all three of these, what we're going to do is we are going to compare f of x sub I delta x, that's right here, to what we've been given, which is right here. So we're going to compare it to 4 over n times 5 plus 4i over n raised to the 10th power. When we compare these two, the first thing we want to notice is that delta x is equal to 4 over n. We'll write down delta x is equal to 4 divided by n. And then we can say that f of x sub I is what's left, and that is 5 plus 4i over n raised to the 10th power. We're now going to simplify f of x sub I by noticing that 4 over n is our delta x. So we're going to substitute that in. So our f of x sub I is equal to 5 plus I delta x raised to the 10th. Now that we have it written this way, we can easily see that x sub I is equal to 5 plus I delta x. And let's go ahead and let's highlight that. Before we go on to find f of x, a, and b, I just want to summarize what we did right here. When you compare the two quantities, you need to find delta x, f of x sub I, and then x sub I. Once you have those three, we can go ahead and find a, b, and f of x. The first thing that we're going to do is we're going to find a. We're going to use the formula that x sub I is equal to a plus I delta x, and we can compare it to what we just found, and we see then that a is equal to 5. Now let's find b. To find b, we have to use the formula for delta x. Delta x is equal to b minus a, all divided by n. And we know from right up here that delta x is equal to 4 over n. So that tells us that b minus a is equal to 4, or b is equal to 4 plus a. And we found that a was equal to 5. So this is 4 plus 5, and we get that b is equal to 9. Now, hang with me. We are almost done. What we need to do now is we need to find f of x. We have the formula f of x sub I is equal to 5 plus I delta x raised to the 10th power. And we know that x sub I is 5 plus I delta x. So that gives us that f of x sub I is just x sub I to the 10th. And then that gives us that f of x is equal to x to the 10th. Now we can write down our answer. Let's go back up and see what we need to find. We want to find the region whose area is equal to this limit. So our answer has to describe this region. So we're going to say that the region is the area under the curve f of x is equal to x to the 10th from x is equal to 5 to x is equal to 9. And there's our answer. This is a hard problem, but now you know exactly how to solve it. And that's it. You've learned how to approximate the area under a curve using right, left, and midpoint rectangles, how to write the area as a limit, and how that limit defines the exact area under a curve. To really master these problems, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.